So let us recapitulate what we have done. In a nutshell, our objective was to show that T minus lambda I is surjective, lambda not equal to 0. We've taken an G in L2, we want to solve the equation 7.15, namely integral 0 to x ft dt minus lambda f equal to G. This integral equation, we found a formula for the solution. What is the formula we obtained? We obtained the formula 7.16, but we obtained this formula 7.16 under the stipulation that G was differentiable. So the derivation of the formula 7.16 is valid only when G is smooth, but now we must prove that it is valid even when G is only in L2. So how do we check that 7.16 works even when G is only in L2? We must directly put it in 7.15. Namely, we must substitute this f in the equation Tf minus lambda f equal to G and see whether we get a correct equation, see whether it satisfies. Okay, so let us do that. So we have to calculate Tf. What is Tf? Remember, what is our f? Our f is minus gx upon lambda minus 1 upon lambda squared integral 0 to x gt e to the power x minus t by lambda dt. We must integrate this from 0 to y. That is your t. What is the Voltaire operator? Integrate, indefinite integral. That's a Voltaire operator. So we integrate this. So Tf of y is minus 1 upon lambda integral 0 to y gx dx minus 1 upon lambda squared. One more integral will come. Integral 0 to y dx integral 0 to x gt e to the power x minus t by lambda dt. Now what is the next obvious step to do? The next obvious step is to switch the order of integrals in the iterated integral that you see in the middle of the slide. So when you switch the order of integration, you have done this numerous times in your bachelor's level courses of switching the order of integration in a multiple integral. And so what do you get? You carry that out. Tf of y equal to minus 1 upon lambda integral 0 to y g of x dx minus 1 upon lambda squared integral 0 to y, first integrate with respect to x and then later integrate with respect to t. So gt dt. The inner integral will be e to the power x minus t by lambda dx. The limits of integration will be t to y. Remember, please work out this in detail. Draw the picture and check that the limits of integration for the inner integral is t to y. Now compute the inner integral. It's an exponential function. You can compute the integral of e to the power x minus t upon lambda dx from t to y. You will get two terms. One of the terms will cancel out. You will pick up a lambda factor and so you will get Tf of y equal to minus 1 upon lambda integral 0 to y gt e to the power x minus t by lambda dt. So we got T of f. Now what must we do? We have to calculate Tf minus lambda f. So calculate Tf minus lambda f and use equation 7.16 again for that purpose. You get your G. And we have verified it. So we have checked that when lambda is not equal to 0, T minus lambda I is surjective. So it's a general fact that the spectrum of any bounded operator on a Hilbert space is always non-empty. In our case, it was a compact operator, but even if the operator is a non-compact operator, if it is a bounded linear operator from H to H, the spectrum will always be non-empty. But the Voltaire operator says that the spectrum can be as small as it possibly can. It's a singleton set. We shall see that this pathology doesn't occur if we have a compact self-adjoint operator. The Voltaire operator is compact, but it's not self-adjoint. We are going to study compact self-adjoint operators on a Hilbert space, and this pathology will not occur. The spectrum will have elements other than the origin, and it will have eigenvalues, and there will be sufficient eigenfunctions for you to form an orthonormal basis. In fact, the spectral theorem holds for compact self-adjoint operators on a Hilbert space, and we are going to prove the spectral theorem in this context. Before we take up this project of proving the spectral theorem for a compact self-adjoint operator, we need to dispose of a few preliminaries, such as we need to introduce a couple of terminology, we have to prove a number of small results, and we shall do that next. First, we need to introduce a new concept called weak convergence of a sequence. So, when does a sequence of vectors in a Hilbert space converge? Take a sequence Vn in a Hilbert space H. We say Vn converges to V in norm if norm of Vn minus V goes to 0 when n goes to infinity. So far, this was the only notion of convergence that we were discussing in a Hilbert space. Now, we weaken this notion, we introduce the much weaker notion of a weak convergence. So, a sequence of vectors Vn in a Hilbert space H is said to converge to V weakly if Vn minus V inner product with W goes to 0 as n tends to infinity. This concept is much weaker than norm convergence. We say that V is the weak limit of the sequence Vn. We say that V is the weak limit. Now, using Cauchy-Schwarz inequality, one can directly check that convergence in norm implies weak convergence. If Vn converges to V in norm, you can deduce that Vn converges to V weakly. Simply apply the Cauchy-Schwarz inequality. The converse is not true. A sequence can converge weakly and it may not converge in norm. Let us see a classic example of that from Fourier series. Our favorite example and our favorite result, the Riemann-Lebeg lemma. Take a sequence sin nx. What does it mean to say that sin nx converges to 0 weakly? Means what? Integral minus pi to pi f of x sin nx dx goes to 0. The inner product there is the integral from minus pi to pi. The weak limit is 0. So, in the definition, V is 0. So, Vn minus V is the same as Vn. So, we have to show that dot product of Vn and W goes to 0 as n tends to infinity. What is my Vn? Sin nx. What is my W? Any element fx. What is the inner product? Integral minus pi to pi. So, our problem is basically integral minus pi to pi sin nx fx dx goes to 0 as n tends to infinity, but that is exactly the Riemann-Lebeg lemma. So, the Riemann-Lebeg lemma says that the sequence sin nx converges to 0 weakly, cos nx also converges to 0 weakly for the same reason. More generally, if you take any orthonormal sequence Bn in a separable Hilbert space, it will converge to 0 weakly. So, I am taking a sequence of vectors Bn, a sequence of unit vectors which are mutually perpendicular. It will go to 0 weakly. Let us do something better. Not only will show that this sequence goes to 0 weakly, we will enlarge the sequence, we will complete it to an orthonormal basis. Remember that a separable Hilbert space has an orthonormal basis. So, this orthonormal set will extend it to an orthonormal basis and will show that the extended sequence itself goes to 0 weakly. Okay. So, at the outset, we may assume that the sequence of vectors is an orthonormal basis. Take a vector V in H and let xj be the jth Fourier coefficient of V with respect to this orthonormal basis Bn. Then what does the Parseval formula tell you? The Parseval formula tells you that norm V squared equals mod x1 squared plus mod x2 squared plus mod x3 squared plus dot dot dot. We have proved this in great detail in this module. So, the infinite series mod x1 squared plus mod x2 squared plus mod x3 squared plus dot 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 converges. So, the nth term must go to 0. So, xn must go to 0. But what is your xn? Your xn is nothing but the inner product of Bn with V, which means that inner product of Bn with V goes to 0 for every V in H, and we established the claim. So, notice that how this is very far from norm convergence. This sequence of orthonormal vectors is far from being a norm-convergent sequence because the distance between any two vectors is root 2. So there is no hope of getting anything converging in norm out of this. Okay, now we must relate the weak convergence and non-boundedness. So now let us prove the following theorem, Theorem 72. Suppose Vn is a sequence of vectors in a Hilbert space converging weakly, then the sequence of norm must be bounded. Sequence of norms must be bounded. What do I mean by that? Norm Vn must be bounded. That is, there is a constant m such that norm Vn less than or equal to m for all natural numbers. In short, weak convergence implies norm boundedness. Conversely, if a sequence of vectors in a Hilbert space is norm bounded, then it has a weakly convergent subsequence. That's the second part of the theorem. This theorem is extremely important, and the first part is a consequence of the Banach-Steinhaus's theorem. We are going to use the Banach-Steinhaus's theorem essentially to prove the first part. The second part is going to be slightly lengthy, and the reason why it is going to be lengthy is because we are trying to give an elementary argument for the second part. But first, let us dispose of the first part. It's a nice application of the Banach-Steinhaus's theorem. So for each n, let us define a linear transformation Tn from H to C by the following prescription: Tn of W equals the inner product of W with Vn. Evidently, it is a linear transformation. It's a bounded linear transformation. Why is it a bounded linear transformation? Let us take absolute value of Tn W, apply Cauchy-Schwarz. You get what? Less than or equal to norm Vn into norm W. Straight away, you say that it is bounded. So we got a sequence of bounded linear transformations. What is the property of the sequence of bounded linear transformation? Tn W converges for each W. That's the definition of Vn converging weakly. That the inner product of W with Vn converges for each W. In other words, Tn of W converges for each W. So Tn of W must be bounded for each W. In other words, the sequence of linear transformation is pointwise bounded. For each W, there is a bound which may depend upon W, namely m sub W. But what does the Banach-Steinhaus's theorem say? There is a common bound m independent of W as long as mod W is less than 1. In other words, the Banach-Steinhaus's theorem says that there is a constant m bigger than 0 such that mod Tn W less than or equal to m for all natural numbers n for all vectors W in the unit ball. That's the Banach-Steinhaus's theorem. So now let us go from there, from this inequality. Mod Tn W is less than or equal to m means what? It means inner product W with Vn less than or equal to m for all natural numbers n. Now take the W to be Vn by norm Vn. Remember that this inequality is only true for W in the unit ball. So I have taken W to be the unit vector Vn by norm Vn itself. So from there you will immediately get that norm Vn less than or equal to m for all natural numbers, and so the norms are bounded. So weak convergence implies norm boundedness, and the proof of the first part is complete. Now let us take the proof of the second part, and you need to be a little patient with this because the proof is long, but it's worth going through this proof carefully. So we shall prove the second part under the additional assumption that the Hilbert space is separable. What is a separable Hilbert space? A separable Hilbert space means that there is a countable orthonormal basis. B equal to B1, B2, B3 dot dot dot. So we have taken a countable orthonormal basis. Now the given sequence Vn is norm bounded. It's norm bounded. So take the inner product of Vn with B1. Apply Cauchy-Schwarz. You will get that this dot product of Vn and B1 is a sequence of real numbers or complex numbers which is bounded. So it must have a convergent subsequence. every bounded sequence of complex numbers or real numbers has a convergent subsequence. So there's a subsequence V and J such that the dot product of V and J with B1 converges to say A1. A1 is a scalar. Now instead of this clumsy subscripts V and J, let us call this subsequence as V11, V12, V13. Let us use double subscript notation and let us use this more convenient representation 7.17. So V11, V12, V13 is a subsequence of V1, V2, V3. Okay. So what is our requirement? Inner product V1n comma B1 converges to A1. Now work with the subsequence V11, V12, V13. Take the dot product with B2. Again I get a bounded sequence of complex numbers. So there's a convergent subsequence. There's a convergent subsequence which will converge to say A2. It is convenient to denote this convergent subsequence by V21, V22, V23, etc. display 7.18. So the vectors in 7.18 form a subsequence of the vectors in 7.17. Keep going in this manner. So what do you get? Each time you get a subsequence and then the next iterate you get a subsequence, subsequence, etc. You get a family of sequences, each being a subsequence of the preceding one. V11, V12, V13, etc. V21, V22, V23, etc. V31, V32, V33, etc. Look at the diagonal sequence. V11, V22, V33. The diagonal sequence will be a subsequence of all of them. The diagonal sequence will have the property that Vnn dot product with Bj will converge for every j and its limit will be Aj by our notation. Now that we have extracted subsequence Vnn, the diagonal subsequence, we must guess what the weak limit is going to be. So we will make an educated guess as to what the weak limit is going to be and we will prove that our guess is correct. So the weak limit is a vector in the Hilbert space and we have an orthonormal basis. So let us express this weak limit W by x1 b1 plus x2 b2 plus x3 b3 plus dot dot dot. Now what do we know? We know that Vnn dot product with Bj will converge to W dot product with Bj by definition of weak convergence. But what is the left hand side? Vnn dot product with Bj we know converges to Aj. But what is the right hand side? W dot Bj is xj. So my xj has to be exactly Aj. So I know what my weak limit is supposed to be. My weak limit is supposed to be W equal to A1 B1 plus A2 B2 plus A3 B3 plus etc. Display 7.20 in the slide. Well, we have guessed what the weak limit is going to be, but there's one small problem. Does the series 7.20 converge in the Hilbert space H? So when will this display 7.20 converge in the Hilbert space? If and only if 7.21 holds. That is if and only if mod A1 squared plus mod A2 squared plus mod A3 squared plus dot 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 less than infinity. That is the condition for 7.20 to even make sense. So now let us verify that 7.21 holds. Let us postpone the verification of 7.21 and let us continue with the argument. Let us assume that the series converges and let's get on. We have to show that for each V in the Hilbert space, Vnn minus W dot with V goes to 0 as n tends to infinity. And this will definitely hold when V is Bj by very construction, because Vnn Bj converges to Aj and W dot with Bj is also Aj. So the requirement Vnn minus W dot V goes to 0 holds when V equal to B1, B2, B3 etc. So it will hold for every finite linear span. So it will hold for every finite linear combination. In other words, it will hold for every element V in the linear span of B. So now let us take an element V in the Hilbert space H itself. But what do you know? we know that the linear span of B is dense in H. So let epsilon greater than 0 be arbitrary. Then there is a finite linear combination of these B's, call this P, such that norm V minus P less than epsilon by 2m. So I have taken an arbitrary element V in the Hilbert space and I approximated it by an element in the linear span of B, which is possible because B is a basis. Where what is M? M is some bound which exceeds norm of W and it exceeds the norm of all the Vn's. Remember our Vn's are norm bounded. Now for this particular P, we know that Vnn minus W dot with P goes to 0. So there exists an n naught such that Vnn minus W dot with P less than epsilon by 2. So now let us proceed. For n bigger than or equal to n naught, what do we have? Vnn minus W dotted with V in absolute value less than or equal to, apply triangle inequality, add and subtract a P, Vnn minus W dot with P plus Vnn minus W dot with V minus P. Apply Cauchy-Schwarz for the second factor, we get norm of P minus V into norm Vn plus norm W, but norm Vn plus norm W is less than m and norm of P minus V is less than epsilon by 2m. So all in all, and the first piece is less than epsilon by 2, and so all in all we get that the whole thing is less than epsilon for n bigger than n naught. Job is done. So what remains in the proof of the main theorem? We have to verify the condition 7.21. Let us go ahead and finish checking condition 7.21 and we'll finish the proof of the theorem. Now proof of 7.21 is a nice application of the parallelogram law, as we shall see. First of all, let us fix some capital N. Let us fix some capital N and let us look at this expression 7.22. Vnn minus twice a1 b1 plus a2 b2 plus etc. an bn norm squared. Now let us expand this 7.22. What do you get? You are going to get three terms. Norm Vnn squared. That norm Vnn squared is bounded by some fixed number because the Vn's are norm bounded. And then the last term, 4 times norm a1 b1 plus a2 b2 plus etc. plus an bn squared. And the middle term, the cross term, we are going to work with real vector spaces for convenience so that the complex conjugation problem is not there. So the cross product, the cross term from the middle will be minus 4 times Vnn dot with a1 b1 plus a2 b2 plus etc. plus an bn. Now let us see what happens when little n goes to infinity. When little n goes to infinity, we know that Vnn into a1 b1 plus a2 b2 plus an bn will converge to mod a1 squared plus mod a2 squared plus mod an squared. And the other term, 4 times norm of a1 b1 plus a2 b2 plus etc. plus an bn squared is also the same as mod a1 squared plus mod a2 squared plus mod an squared. So these two things cancel out. In other words, what we are left with is that 7.22 as n goes to infinity simply is bounded by the common upper bound for norm Vnn squared. So now we are ready to apply the parallelogram law. So let us take capital X to be Vnn minus a1 b1 plus a2 b2 plus etc. plus an bn. Take capital Y to be a1 b1 plus a2 b2 plus an bn. So that x plus y will be what? X plus y will simply be Vnn. And what does the parallelogram law say? Norm of x plus y squared plus norm of x minus y squared equal to 2 times norm x squared plus 2 times norm y squared, which means 2 times norm y squared is less than or equal to norm of x plus y squared plus norm of x minus y squared. But what is norm of x plus y squared? Norm Vnn squared. What is norm of x minus y squared? That is 7.22. We have just seen that 7.22 remains bounded. And so norm y squared remains bounded which is exactly what we wanted to prove. So now let us look at what is norm y squared. This expression norm of a1 b1 plus a2 b2 plus etc plus an bn squared remains bounded. Expand this out. Bn's are orthonormal. You're going to get mod a1 squared plus mod a2 squared plus mod a3 squared plus dot 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 plus mod an squared is bounded by fixed number a for all capital N, which basically means that the expression 7.21 is finite. We have completely checked the correctness of 7.21 and the proof of the theorem is thereby completed.